In the previous video, we introduced proportional control and on-off control. On-off control results in continuous cycling of the manipulated and the controlled variables, whereas proportional control can lead to a new steady state. However, if there is a sustained input deviation or deviation in the measured variable, then proportional control can lead to what we call a steady state offset in the controlled variable. We showed this by considering what happens to the gravity-driven flow out of a tank with a proportional-only level controller. And we showed that when there's a sustained deviation in Qi, there must also be a sustained deviation in Q for the system to reach a new steady state, so that at the new steady state, the Q equals the new Qi. For Q to be different from its steady state design condition, the valve must be further open or further closed than the steady state condition, which must mean that the error signal is non-zero. That is, at the new steady state, the controlled variable is not equal to its set point. We call this phenomenon steady state offset. To improve the controller action, and often to eliminate steady state offset, the controller output can be made to depend upon the integral of the error. Integral controllers compute the controller output by adding the bias to the integral of the error signal, where tau I is a controller tuning parameter called the integral time or the reset time. The advantage of using integral control is that the controller output signal P of t will always be changing with time unless the error signal goes to zero. When the error signal goes to zero, the integral stops changing with time, and the controller output can stop changing with time. Because the controller output won't stop changing until the error goes to zero, integral control can help eliminate steady state offset. A disadvantage of integral control is that the controller doesn't take action immediately when the error is non-zero. The controller only takes action after the integral of the error with respect to time has accumulated. Therefore, integral action is usually combined with proportional action, where the proportional element can respond immediately to changes in the error signal, and the integral action is a slower response that can be used to eliminate the steady state offset. We combine proportional and integral control by adding a proportional element to an integral controller in the time domain. To find out what this looks like in the Laplace domain, we'll find the transfer function for the PI controller, or the proportional integral controller. We first define deviation variables, and then we take the Laplace transform of the PI controller equation, which has a proportional component and an integral component. We then factor out the error signal and divide by the error signal to derive the transfer function relating the controller output to the error signal input. These are two equivalent forms of the transfer function for a PI controller. The controller output signal for a PI controller in response to a step input in the error signal contains a constant term represented by the response of the proportional part of the controller to the step input, and a ramp represented by the response of the integral part of the controller to the step input. The proportional part responds immediately when the error signal changes, and the integral part continues changing with time because we have a sustained non-zero error signal. When this is in a feedback control scheme, as the controller output changes, this process hopefully brings the error back to zero. So we'll learn more about the dynamics of controlled processes later. But for now, it's important for you to know that PI control can lead to oscillations in the controlled variable. Because integral controllers take time to respond, the controlled variable often oscillates. The controller must be designed so that the oscillations are small and so that those oscillations decay with time rather than growing with time. An intelligent controller might also respond differently when a disturbance is rapidly changing than when a disturbance is slow to change. The PI controller does not respond more quickly to rapid changes than to slow changes. This can be remedied with what we call PID control. We'll discuss PID control in the next video.